It was author Faith Baldwin who said, "Time is a dressmaker specializing in alterations." In this lesson, we're going to construct exponential and logarithm models for a situation. We're going to evaluate logarithms. We're going to express exponential models as logarithms, demonstrate use of change of base formula, and evaluate a common and natural logarithm. All to answer the question, how long should funds remain in a single deposit savings account? Before we begin, let's make sure we're ready for this lesson by looking at warm-up number 2 and solve for x in each of the following exponential equations. Well, we have a hint about 512. So 8 times 8 would be equal to 64. If I multiplied that by 8, I would get 512, meaning that x is 3. If we look at 1 over 36, that would be 36 to the negative 1 power. Now, 36 is the same thing as 6 squared, and that is also to the 1/2, meaning we have 6 to the negative 2 power, so we can see that x is negative 2. Pi to the x power being equal to 1, we know that anything raised to a 0 power is equal to 1 as long as that thing on the base is not 0, so x is equal to 0. Now, let's take a look at a problem that you will be able to do by the end of this lesson. Pete deposited $8,000 into an account that compounds continuously at a rate of 3.7%. How long will it take his money to grow to $10,000? Now, we know the equation that we're going to use is b is equal to p times e to the RT power. We know that the ending balance desired is $10,000 with an initial investment of $8,000 at 0.037 for our rate. We can substitute all of those values into the equation, divide both sides by 8,000, take the ln of both sides. Now, this exponent up here does mean that we could rewrite this as 0.037t times ln of e. And let's remember that ln of e is equal to 1. So ln of 1.25 divided by 0.037 will be equal to t, and that is approximately 6.03. When a customer opens a single deposit savings account, such as a CD, the single deposit is made to an account and remains invested for a specific period of time at a specific rate of return. As discussed in earlier lessons, the length of investment time is known as maturity, or term. CDs can be short-term with maturities of a few months or long-term with maturities of a number of years. In lessons of this unit, we've explored formulas for investing in a variety of savings situations. In the examples given, we looked at the monetary value where the investment rate and the term were given in the problem stated. But typically, this is not the case when consumers choose a CD best to meet their savings goals. Consumers need to study the investment rates and terms for an account before making the initial investment. Often, they're faced with a difficult decision of how to lock into a savings agreement. Banks usually offer a variety of CD accounts with varying maturities. A consumer's decision on which account to choose may be dependent upon the number of factors which will influence that choice. For example, someone knows that they will be needing the money to pay off a student loan in 4 years. An account with a term beyond that would not meet their needs. Examine the formula that was used to find the future balance B of a single deposit investment P, where R is the interest rate expressed as a decimal, N is the number of times the interest is compound annually, and T is the term of the account. Notice that the term or maturity variable T is in the exponent. Suppose the consumer wants to determine the term of an account based on a fixed values of the variables B, P, R, and N. Traditional mathematical inverse operations that you have learned in previous courses, such as addition or undoing subtraction and multiplication or to undo division, will not work here in order to solve for variable T. In this lesson, you will learn how to use new inverse operations in order to be able to solve for the exponent in an exponential equation. The maturity variable t in the compound interest formula can be treated as a dependent variable in situations where the principal, interest rate, account balance, and the number of yearly compounding periods are all independent variables. Here we explore ways to solve for exponential variable in order to determine the maturity of a specific savings account. After putting values for B, P, R, and N, the compound interest formula for Anna's account is $1,061.51 is equal to 1,000 times 1.01 to the 2t power. Determine the interest rate for this account expressed as a percent. We already know the formula that we're going to be using, and we already, for the most part, know the value of some of these variables. But 1 plus r over n gives us 1.01. That means that r over n must be equal to 0.01. And knowing that n times t is 2t, this means that n is 2. Given these two pieces of information, then r over 2 would be equal to 0.01, meaning the interest rate would be equal to 0.02 or 2%. Let's check our understanding of this. Andy's savings account balance is $2,148.85. He started with a principal of $2,000. After putting in variables B, P, R, and N, the compound interest formula for Andy's account is shown here on the screen. Determine the interest rate for the account expressed as a percent. So we know the formula that we're going to use, and we know the value that goes into different parts of the formula. From 1 plus r over n being equal to 1.006, then we can see that r over n must be equal to 0.006. Also, nt being equal to 4t means n equals 4. This means 0.006 is equal to r over 4. Meaning the R is 0.024 or 2.4%. Let's extend our understanding of this, and after inputting the values B, P, R, and T, the compound interest formula for Kate's savings account is shown on the screen. The interest rate for the account is 0.8%. How many times per year is the interest compounded on this account? Well, 1 plus r over n is 1.002, which means that r over n is 0.002. Knowing that the interest rate is 0.8%, so we get 0.008 divided by n is equal to 0.002, meaning we get 0.008 divided by 0.002 will equal n, so it compounds quarterly. Since the compound interest formula takes the form of an exponential equation, you can solve for an exponent by rewriting it as a logarithmic equation. A logarithm, or log, is defined as an exponent indicating the power to which a base number is raised to produce a given number. In rewriting the exponential equation as a logarithmic equation, you are able to solve for the exponent. In general, an exponential equation has the form a is equal to b to the c power, where b is greater than 0. Can be written as a logarithmic equation. C is equal to log b of a, and reads as C equals logarithm of a with base b, or C equals log base b of a. Since the base b must be greater than 0, it follows that a will be greater than 0 or equal to 0 as well. It is important to note the following special logs. Log base b of 1 is equal to 0, since b to the 0 power would be equal to 1. Log base b of b is equal to 1, since b to the first power is equal to b. Log base b of x is equal to x, since b of x is equal to b of x. Examine these logarithm equations and their logarithm equivalents. 7 squared is equal to 49. It gives us log base 7 of 49 is equal to 2. 25 to the half power is equal to 5 gives us log base 25 of 5 is equal to 1/2. We can see that a to the bc power is equal to d gives us log base a of d is equal to bc. This gives us log base a of d divided by b is equal to c, and log base a of d divided by c is equal to b. In the examples that follow, we're going to use logarithms to solve for exponential variables using the maturity of a savings account. Let's construct exponential and logarithm models. Let's rewrite Anna's exponential compound interest equation from the first example as a logarithm equation and write an expression in terms of t. Now the equation we had was 1061.51 is equal to 1000 times 1.01 to the 2t power. So the first thing we're going to do is divide both sides by 1000. This is going to give us 1.06152 is equal to 1.01 to the 2t power. This means that log base 1.01 of 1.06152 would be equal to 2t, and that log base 1.01 of 1.06152 divided by 2 would be equal to t. Let's check our understanding of this and use logarithms to write an expression for the term t in the compound interest formula. So first we're going to divide both sides by p, giving us b divided by p is 1 plus r over n to the nt power. Now we're going to convert this to a log by saying log of 1 plus r over n of b over p is equal to nt. This means that log base 1 plus r over n of b over p divided by n would be equal to t. Let's extend our understanding of this and rewrite the following log into an exponential form. So the first thing we're going to do is multiply both sides by 5 so that we can get 5t is equal to log a of 1000. Something I like to keep in mind as a simple translation is 2 to the third power is equal to 8, meaning log base 2 of 8 equals 3. And we can follow this in either direction so that 5t equals log base a of 1000 will give us a to the 5t power equals 1000. Now in example 2, we found the maturity t for an account expressed as a logarithm with a base of 1.01. Most calculators do not have an easy log key for bases other than 10. A logarithm that has a base of 10 is known as a common logarithm. Such logs are usually written without expressing the base 10. For example, log 100 means log base 10 of 100. The common log key on the calculator allows you to evaluate this logarithm. Using your calculator, you would be able to find log 100 is equal to 2, as you would expect, since 10 squared is equal to 100. If you know the value of log x, you're able to determine x, which is known as the antilog. For example, we know that log 100 is equal to 2 and log 1000 is equal to 3. Therefore, log x, where 100 is less than x less than 1000, must be equal to a number that is greater than 2 and less than 3. Pick any number between 100 and 1000 for x and find the common log of the number. The results will be between 2 and 3. For example, log of 150 is 2.176091259. Log of 500 is 2.69897004. And log of 999 is 2.999565488. Common logs are easy to use and understand. You can use the common log key on your calculator to evaluate logarithms, such as log base 464, by employing what is known as the change of base formula. This formula is stated as follows on the screen. Since a can be a value greater than 0, let a equal 10. The logs in the fractional part of the equation are now common logs. The change of base formula now looks like this. Using the change of base formula facilitates finding numerical value of a logarithm on your calculator as shown. Log base 4 of 64 is equal to log of 64 divided by log 4, which is 3, since 4 to the third power is 64. Log base 25 of 5 is equal to log of 5 divided by log of 25. That's equal to 1/2, since 25 to the 1/2 power would be equal to 5. And log base 1/3 of 3 is equal to log of 3 divided by the log of 1/3. That's equal to -1, since 1/3 to the -1 power is equal to 3. Now let's demonstrate the use of change of base formula and let's evaluate logs. In example 2, the logarithm part of the solution is given as log base 1.01 of 1.06152. Use the change of base formula and your calculator to determine the value of this expression. Round your answer to the nearest integer. Then use this result to find the value of t in terms of this account. So t would be equal to the log base 1.01 of 1.06152 divided by 2. This means we would have log of 1.06152 divided by log of 1.01 all over 2. To do this on a TI-30XA, what I would do is put 1.01 and hit log. Now I get an inconvenient number, so I put stow1. Now 1.06152 log, I get a number, divide, recall 1, and hit equals. That's done the entire of the numerator, which means I have approximately 6 divided by 2, which is approximately now 3. On a more sophisticated calculator, such as the TI-30XS, I could use the fraction button and put a fraction in the numerator. From there, I can say log 1.06152, close that parenthesis, and go down arrow. Log 1.01, close the parenthesis, down arrow, 2, and hit enter. Now that 2.999992871, that's still approximately 3. Let's check our understanding of this, and after solving for t in a compound interest formula, we find that t is log base 1.0005 of 1.03044 all over 12. Let's use the change of base formula to find the value of the term of the savings account and round the answer to the nearest whole year. If we assume that we're using a less sophisticated calculator, then we're going to want to calculate this denominator first. So 1.0005 log stow1 to put that into the calculator's memory. Now 1.03044 log divide recall 1 equals, and that's the numerator, but don't forget to put that divide 12 equals. We get 4.9988, which means all of this is approximately 5, since we're rounding to the nearest whole year. Now, let's express exponents as logs. Nancy and Bob want to renovate their kitchen sometime in the future. They've deposited $16,000 into an account that compounds interest monthly at a rate of 2.4%. How long will it take the account to reach $20,000? We already know the equation that we're going to want to be able to use. So we substitute all of the values into that equation. We do a little bit of calculation by dividing both sides by 16,000. We also do 0.024 divided by 12. We then combine those like terms to get 1.25 is equal to 1.002 to the 12t power. This means that log base 1.002 of 1.25 is equal to 12t. This gives us that log base 1.002 of 1.25 divided by 12 is t, which gives us log of 1.25 divided by log of 1.002, all divided by 12. Which means we're going to approximately get 9.3 as the number of years. Let's check our understanding and see if Rudy deposited $500 into an account with 1.2% interest compound quarterly. How long will it take for that amount to double? Now, we know our formula and almost all of the variables. The end balance that we want is twice the amount that's put in, which means we want $1,000 coming out. I prefer to manipulate the equation without the numbers first. This means that b over p is equal to 1 plus r over n to the nt power because we divided both sides by p. So we get log base 1 plus r over n of b over p is equal to nt, which gives us log of b over p over log of 1 plus r over n all divided by n. We can substitute all of our known variable values. So we have log of 1,000 over 500 divided by log of 1 plus 0.012 over 4, all divided by 4. This means that t is approximately 57.8 years. So let's extend our understanding of this, and Myra deposited $D into an account at 2.8% interest compounded quarterly. How long will it take for that amount to double? We know what the beginning equation was and what most all of the values were, so we can fill those in. But the end balance is twice whatever the beginning balance was. So I just used 1 for every $1. We want $2 out. And we know from the last example that we're going to get t is equal to log of b over p divided by log of 1 plus r over n all divided by n. Which means by substituting in the values we know for all of the variables, we can find that t is equal to approximately 24.8 years. In the lesson on continuously compounding, we were introduced to the formula for continuous compounding. B is equal to P times E to the RT, where B is the ending balance, P is the principal, and E is the exponential base. R is the interest rate expressed as a decimal, and T is the term of the account. The function f of x is equal to e to the x is known as a natural exponential function. This exponential function can be expressed in terms of a logarithm as x is equal to log base c of f of x. A logarithm with a base e is known as a natural log and is written ln f of x. Using a natural log, the continuous compounding formula can be solved for maturity t as follows. B is equal to p times e to the RT, which gives b divided by p is equal to e to the RT, which means RT is equal to log base e of BP, or that t is equal to log base e of BP divided by R. Expressing this as a natural log would be t is equal to ln b over p all over R. It's important to note the following natural log values. ln of 1 is equal to 0 since e to the 0 power is 1. And ln of e is 1 since e to the 1 is 1. And ln of e to the x is x since e to the x is equal to e to the x. It's easy to make calculations using a natural log since most calculators have a natural log key. Now let's evaluate common and natural logs, specifically here a natural log. Pete deposited $8,000 into an account that compounds continuously at a rate of 3.7%. How long will it take his money to grow to $10,000? Now we know the equation that we're going to use is b is equal to p times e to the RT power. We know that the ending balance desired is $10,000 with an initial investment of $8,000 at 0.037 for our rate. We can substitute all of those values into the equation, divide both sides by 8,000, take the ln of both sides. Now this exponent up here does mean that we could rewrite this as 0.037t times ln of e. And let's remember that ln of e is equal to 1. So ln of 1.25 divided by 0.037 will be equal to t, and that is approximately 6.03. Let's check our understanding of this and see how long it would take for the money from example 5 to double. This means we know exactly the formula that we're going to use. We're going to start out with an $8,000 investment with a rate of 0.037. The end balance that we're after is $16,000. Now the truth is, I don't use these numbers. I act like for every $1, we're going to get $2. But doing the calculation in either way will work. This means that 2 is equal to e to the 0.037 t power, or that ln of 2 is equal to ln of e to the 0.037 t power. The right side can be rewritten as 0.037t times ln of e. Let's not forget that ln of e is equal to 1, meaning that gets to go away nicely, giving us ln of 2 divided by 0.037 is equal to t, or approximately 8.7 years.